again. I would like today to talk about how anthropocentric thermodynamic is. And this is something that comes up a lot in the discussion, mainly in the context of statistical mechanics, where we have this big debate about whether the Gibbs entropy or the Boltzmann entropy is the correct generalization of thermodynamic entropy. But when we look a bit closer at the topic, we see that this debate already has its origin in thermodynamics itself. So today I will be talking mainly about thermodynamics. I will, towards the end of the talk, maybe go a bit into quantum statistical mechanics or make some remarks. But I'll try to stick with the thermodynamic entropy and be clear when I'm not talking about the thermodynamic entropy throughout. Okay, so we see, especially from philosophers of physics, a lot of criticism about how entropy sometimes is construed as mind-dependent or as anthropocentric or as subjective. And here is one of those, one example is by Doherty and Callender in their paper about black holes and the thermodynamic nature of black holes, or their argument against the thermodynamic nature of black holes, where they write, look, a steam engine's efficiency doesn't care about whether anyone is looking, our uncertainty, or our beliefs. So this is a very strong statement against the proposition that thermodynamics has something to do with the mind or is in some sense subjective. We have here this wonderful quote by David Albert, of course, where he talks about the statistical mechanical entropy, but it is based on beliefs about the thermodynamic entropy ought to be objective. And David writes, can anybody seriously think that it is somehow necessary that the particles that make up the material world must arrange themselves in accord with what we know, with what we happen to have looked into? Can anybody seriously think that our merely being ignorant of the exact microconditions of thermodynamic systems plays some part in bringing it about, in making it the case that, say, milk dissolves in coffee? And underlying is this idea that thermodynamics is about the efficiency of steam engines, it's about work, heat, and entropy. You know, if I burn myself on a hot plate, it is because there's something real about the hot plate being hot, about heat being transferred. What should the mind or what should the subject have to do with any of this? Now, on the other hand, we have people who suggest that there is something very mind-dependent or very anthropocentric about thermodynamics. So here is Bridgman, who writes, thermodynamics smells more of its human origin than other branches of physics. The manipulator is usually present in the argument, as in the conventional formulations of the first and second laws in terms of what a manipulator can or cannot do. So the subject here enters into the theory, or at least according to Bridgman. And when we go further back in history, we see that already Maxwell thought about thermodynamics in terms of agents, in terms of what we can and can't do with agents. Here he writes, confusion, so he's talking about heat, like the correlative term order, is not a property of material things in themselves, but only in relation to the mind which perceives them. So we see that for Maxwell, apparently, or it seems as if the subject here enters quite clearly into the thermodynamic theory. But you have Jaynes, who of course is notoriously famous for his epistemic approach to statistical mechanics, in particular his epistemic interpretation of the Gibbs entropy, who writes, the strong contrast between the physical nature of energy and the anthropomorphic nature of entropy was well understood by Gibbs before. So now even Gibbs enters into the picture. So we have these three fairly well known physicists, or four, Maxwell, Gibbs, Jaynes, and Bridgman, and many others, especially today in the realm of quantum information theory, that think there's something inherently anthropocentric about entropy. The mind or the agent plays a crucial role in our understanding of entropy. Now what I'd like to do today is I'd like to chase the human smell. I'd like to figure out where does this idea of anthropocentrism enter the theory. And the way I'm going to approach this, I'll have one slide just for clarity about what I mean by objectivity, what I mean by anthropocentrism. This is not to spark a debate about the nature of objectivity. This is just so that we are all on the same page, and I can communicate a bit better what was motivating me, and my co-author Katie Robertson, with whom this is very much a joint project. I should have said that before. I go into the laws of thermodynamics a bit. I point out that there are actually 2 second laws that have been identified after the discovery of the kinetic theory of gases. And then I go into a bit more into the means relative approach to thermodynamics and explore where exactly the minds, the agents, the knowledge, the information enters into classical thermodynamics. I do that by considering the Gibbs paradox and offering a solution that was given by Gibbs, but also by Maxwell, and afterwards famously by Jaynes to the Gibbs paradox. And I'll make a bit more explicit how we get from a means relative approach to thermodynamics to a knowledge-based approach. Finally, I will argue that we can actually have our cake and eat it too, which means that we can keep all the benefits from the means relative approach to thermodynamics without having to commit in any way that thermodynamics is anthropocentric. And finally, if there is time left, I'll start looking a bit more into the quantum statistical mechanics approach to thermodynamics, and just to give an idea of how we can even understand the statistical mechanical case in these means relative terms. Okay. So I'm going to begin with by introducing 2 types of objectivity. The one is objectivity understood as an intersubjective agreement. This is very much like the objective in objective Bayesianism. This means that 2 agents agree on that there's an intersubjective agreement about a proposition. The second type of objectivity is something is objective if it is independent from mind perspective. And this is, when I talk about anthropocentrism, I very much talk about the denial of the second type. So I mean by this, when we talk about heat and work and entropy, and we consider them to be defined in relation or relative to the mind or to its perspective, then this would be anthropocentric. Okay, so I will just for completeness begin with the laws of thermodynamics and begin with the arguably most fundamental law of thermodynamics, the minus first law, as was coined by Brown and Uffing. Minus first law states that an isolated thermodynamic system in an arbitrary initial state within a finite fixed volume will spontaneously attain a unique state of equilibrium. So it posits the conditions that there have, for thermodynamics to work or to apply, or for the thermodynamic theory to be able to kick off. We're going to need the existence of equilibrium states. We're going to have to these equilibrium states need to be unique, and there needs to be a spontaneous approach to equilibrium states. Now, the reason why we need this is because for the second law, for example, we're working in a thermodynamic equilibrium state space, which means that all points in our state space are equilibrium states. But of course, a system once at equilibrium is not going to leave equilibrium, at least according to classical thermodynamics, which means that we're going to need to nudge the system in a slight way, and then in order for it to reach another equilibrium state, we're going to need these conditions to be fulfilled. So the minus first law is very much working in the background of thermodynamics. So let's then take a look at the first law of thermodynamics. The first law of thermodynamics states that the internal energy of a closed system can only change by adding heat, delta Q, to the system, and or by performing work, delta W. And these deltas are just, I wrote delta, like these are inexact differentials. Oops. And okay, I've done something. There we go. So the way we define work, or the way I define work, is as the transfer of mechanical energy. So that could be the raising or the lowering of a weight. Another way of characterizing is by saying this is the usable energy. This is very much what Maxwell did, and we'll come back to this in a bit. And heat then is the transfer of non-mechanical energy. So it does not involve the raising or the lowering of a weight. In other terms, it's unusable energy. So every now and then, so here it's already, with usable and unusable, we're already implicitly assuming that there's an agent. So whenever there's like this little guy here showing up, then that means like something anthropocentric. Well, no, some human smell is here. It doesn't mean necessarily anthropocentric, but we have this human smell here for sure. So the first law then just states that the energy change of a system is characterized by the amount of heat the system exchanges with its environment and by the amount of work that's performed on by the system. So I assume like most of you already know this stuff. The reason I'm discussing it again is just so everybody's on the same page, because it turns out that the way we phrase the second law and the first law already gives us, already pushes us into several directions about its interpretation later. Another way of understanding the first law is that it restricts the types of processes a system can undergo to those that conserve energy, which is why the first law is often also coined the conservation of energy in systems. Now let's move on to the second law, and I'd like to start with the very origins of the second law, which is Carnot's theorem. So Carnot still thought that heat was something like a liquid, something that conserved quantity, but he still managed to come up with this wonderful theorem about efficiency, which states that take two reservoirs, one at a higher temperature and one at a colder temperature, and then all heat engines operating between two reservoirs are less efficient than a reversible heat engine. And the second part of the theorem states that all reversible heat engines operating between two reservoirs have the same efficiency. Now this in particular implies that the maximum efficiency of a heat engine is independent of the working medium we use. And this is something that we often use as a reason for treating thermodynamic systems as black boxes. So this is very much the framework in which will pop up later as well. The idea that a thermodynamic is a black box because the laws of thermodynamics, or the second law at least, tells us that we can treat thermodynamic systems, that the maximum efficiency of the thermodynamic system is independent of the working medium we're using. Which means we don't care about what the thermodynamic system consists of, whether it consists of many molecules or like monatomic or diatomic molecules. This is of course all idealized. I mean, there are limitations to this, to how black boxy it can get. So Clausius then observes that heat everywhere exhibits the tendency to annul differences of temperature, and therefore to pass from a warmer body to a cooler one. Now this is an empirical statement. This is a phenomenon that has been observed, that is informing that is the foundation of the second law itself. So yes, empirical observation. And then finally, the second law, as we all know and love it is impossible to perform a cyclic process which is no other result than that heat is absorbed from a reservoir with a low temperature and emitted into a reservoir with a higher temperature. This is the Clausius statement. There is also the Kelvin statement that you might be familiar with. And it just, sorry, I don't know why, like, this is the wrong heat engine I wrote there. But, like. So the problem with the second law is when the kinetic theory of gases, when we started to realize that thermodynamic systems gases are made out of molecules that are bumping into each other. And we started, I say we, I mean I didn't really do this, but again physicists started to identify the average kinetic energy of the molecules with the temperature. We were all of a sudden, thermodynamics was already all of a sudden facing something like a little crisis. And the reason it did so was because if you look at subsystems of your gas and you look at the average kinetic energy of a subsystem of your gas, you will see that the kinetic energy of this subsystem might differ from the kinetic energy of the other subsystem. Now this means that effectively you will see that at one part of the gas is at a slightly different temperature than another part of the gas. And this seems to be at least a straightforward violation of the second law. Because the second law, as we earlier saw, empirical observation tells us that heat flows in such a way so as to annul temperature differences. Here it seems to be that the temperature differences are created constantly within a thermodynamic system. So I put here a question mark at violation of the second law because it depends on how you understand the second law to be. So in order to make this more explicit, Maxwell invented his famous Maxwellian demon. We earlier saw that the second law was phrased in terms of cycles, in terms of cyclic operations. So what Maxwell then did to illustrate his point about why the second law is violated, he said, like, imagine now we have a little powerful being that was able to track the movements of the molecules. And the being was able to, and we separate the gas with a partition and a little trapdoor, and the being is able to operate the trapdoor. And now the being, or the little demon, is opening the trapdoor for the fast molecules coming from the right, and he's closing it for the slow molecules coming from the right, and he's opening it for the slow molecules coming from the left, and closing it for the fast molecules coming from the left. And then in the end, the demon will effectively have separated the gases into a hot gas and a cold gas. It will have separated the gas itself into a hot subpart and a cold subpart. And now the demon can use operations to extract heat and to extract work from the system and effectively violate the second law. So a good way to think about the consequences of Maxwell operations is to look at the original second law. It's impossible to perform a cyclic process with no other result than that heat is absorbed from a reservoir and work is performed. Now this is the Kelvin statement of the second law. And then realize that we have now two choices when faced with a Maxwellian demon or when faced with Maxwell's thought experiment. The first one is to consider the second law as a statistical second law, and this is very much what Maxwell did. He said, look, the second law is a statistical rather than a mathematical truth that holds for macroscopic systems. So de facto, we can't violate the second law, but for Maxwell, a Maxwellian demon could in fact violate it. Another option is to understand it in probabilistic terms and say, look, we're going to amend the content of the second law, and we're just going to say the second law prohibits the reliable conversion of heat into work from a single reservoir. This is made precise by the notion of expectation values. So you might, if you're an agent, you might be able to, let's say you have a box of gas and you arbitrarily insert a condition, and there turns out to be a fluctuation. You might be able to every now and then extract a little bit of work from it, but you won't be able to do that on a regular basis. And there's like Wade-Mervold and O'Maroni have made very similar points in their papers about this. Now these strategies are very different. Like here, what we're doing is we're effectively changing the scope of the second law. We're now restricting ourselves to macroscopic systems, to systems containing a lot of molecules, so that Right, so that, in principle it's impossible to, in practice it's impossible to violate the second law. Not really, but it could still be violated every now and then. Whereas the probabilistic second law changes the content of the second law. So now we're including this, including the condition that now we're talking about the reliable conversion of heat into work from a single reservoir. So you might be able to extract a bit of work from a reservoir every now and then, but you're not going to be able to do that on a reliable basis. Now for this one, to make this precise, we're going to need expectation values, which is, we're going to need to use probabilities. We're not talking about averaging over individual molecules of a gas, but we're now averaging over cycles, which turns out to be a bit, well, philosophically or conceptually a bit more difficult to justify without making reference to uncertainty or without getting into trouble by trying to interpret the probabilities. So for this, here is another way where the human smell enters. This one, on the other hand, here is a problem that before we were talking about thermodynamic systems as black boxes, but now all of a sudden we make conditions on the content of the black boxes. So that's like a bit amiss as well with the spirit of thermodynamics, traditional thermodynamics. One interesting fact that might be is, I think people who are more following along in the statistical mechanical lines along the Boltzmannian approach would probably say this is the way to understand the second law, whereas those who are more Gibbsian would probably say we should understand the second law as in its probabilistic form. But the two are distinct, and I think a lot of the debate and a lot of the seeming animosity between Gibbsians and Boltzmannians is actually unfounded, because we're really talking about very different things in a lot of these cases. Now Maxwell, as I just mentioned, was a proponent of the statistical second law, but not only that, he also understood the second law as being defined relative to our means. So he says, the second law is equivalent to a denial of our power to perform the operation just described to transform heat into ordinary motion, either by a train of mechanisms or by any method yet discovered. Hence, if the heat consists in the motion of parts, the separate parts which move must be so small that we cannot in any way hold of them to stop them. So this is very much about our limitations and as human beings. And I think there's also this famous quote where Maxwell says, the second law is that the second law cannot be violated is akin to the statement that you cannot throw a tumbler full of water into the ocean and retrieve the same tumbler full. Is it that tumble or tumbler full? I don't know. Like you throw glass into the ocean and you can't retrieve the same glass with exactly the same molecules that you threw in. I mean, you can in principle, but in practice it's basically impossible. Okay, so just going back to the second law now. It is impossible to perform a cyclic process which has no other result than that heat is absorbed from a reservoir with a low temperature and emitted into a reservoir with a higher temperature. Now this could be understood, as you just said, like as a nomological truth, like this impossibility that we have in the second law. We could say like this is a strict impossibility, and like this is not allowed according to the laws of nature, or it's a practical impossibility, which means like it is, like in principle it is possible, but in practice it isn't. And the moment we start talking about in practice, we start talking about means, about agents, about beliefs. So this is very much where the anthropocentric aspect enters the history of thermodynamics. And I'll take a closer look at this part now. So Maxwell was as I said, was a strong proponent of what he considered means relative approach. And he writes, confusion like the correlative atom or the sort of property of material things. We saw this we saw this earlier, and Wayne Merwold, who wrote this wonderful paper about Maxwell's view on thermodynamics, interprets this as saying that the distinction between heat and work that Maxwell makes seems to rest on anthropocentric considerations, or better, on considerations of the means we have available to us for keeping track keeping track of and manipulating the molecules. So he reads Maxwell, as Maxwell writes, and he says, the distinction between human work rests on anthropocentric considerations, on considerations that have something to do with our mind and our abilities, and he equates this with the means we have available to us for keeping track of and manipulating the molecule. So the Maxwell's means relative approach does have something for it. So one thing that makes it very attractive, it not only does it, well, according to Maxwell, we make the Maxwellian demon less problematic, but it also helps us with the notorious Gibbs paradox. Now, the Gibbs paradox is the following. If we have two gases separated by a partition, and we remove the partition, and we insert it again, we will have an increase in entropy. Now, if we have two gases that are identical, then and we remove the partition and we insert it again, we don't have an increase in entropy. Now, the paradoxical thing is that no matter how similar these gases are, they could be similar in all kinds of respects. They could be similar, they could be the same in all thermodynamically relevant aspects. They could even have the same trajectory, but if there is something that is slightly different about them, then we see this increase in thermodynamic entropy. And this is in a way paradoxical. So you can imagine you have two gases. One of them just has this really strange, undergoes a strange reaction with kryptonite. The other one doesn't. But for us, there is nothing that distinguishes them. And then we would see if we remove the partition and we insert it thermodynamics, we predict an increase in entropy, whereas if the gases are identical, we wouldn't see an increase. So now there are like many resolutions to the Gibbs paradox, and Simon Saunders at Oxford has offered some as well. But the Rien's relative approach is, at least in our understanding, quite elegant for this. It says, now let's just look a bit closer at what we understand a thermodynamic state to be. We said a thermodynamic state is characterized by a set of macro variables, and the entropy is a function of those macro variables. And the idea is that if you have the means to distinguish between the gases, then you would be able to extract energy from this scenario. So you would be able to extract energy from the gas in terms of work. If you don't have the means, you're not. So the idea here is that the gas undergoes the gas is the set of variables you assign to the gas are defined in terms of your means, which means that two observers could assign a different state to the gas. And it could even be the case that, imagine I'm characterizing my state, the state of the gas in terms of the thermodynamic variables x1 to xn, and Alice is characterizing the state of the gas in terms of thermodynamic variables x1 and until xn plus 1, so she knows something more about the gas. Well, I'm using knowledge now, but let's just assume she knows, or she has a means to distinguish between the molecules of gases. Then Alice could extract work from the gas, whereas I couldn't. So for me, it would seem as if the second law is violated, because she's just extracting work from a gas, that for me appears to be completely identical. But for her, of course, the second law is not violated. All she's doing is she's inserting a semi-permeable membrane and extracting work from the system. And the reason that the entropy in this case here is rising is by removing the partition and reinserting it. You're in a sense wasting your knowledge. You made a gas that could have been exploited where we could have extracted work from into a gas that is now useless for work extraction. this is why Maxwell says like the entropy increases. So he writes, to say that two gases are thermodynamically the same is just to say that one cannot distinguish the one from the other by any known reaction. Right, okay, so the means and the knowledge determine what operations can be performed on the gas, on the system, and different agents may assign different states to the system. Now, where does anthropocentrism come into this? So the chain of reasoning that's been done by Maxwell and then later on by Gibbs and by Jaynes and by Wayne Morwold, who was analyzing Maxwell's work, is look, heat, work, and entropy are means relative. They're defined in terms of like relative to the means we have available, relative to the knowledge we have available of the gas, or of the thermodynamic system, I should say. Now the means themselves, yeah, they are determined by what an agent knows or can know. And then the final step is that, well, now we're talking about knowledge, so this means that the knowledge in some way has to be fundamental to thermodynamics in virtue of the knowledge determining the means, which in turn determines heat, work, and entropy. And this basically leads to the conclusion that heat, work, and entropy are anthropocentric. And here is Jaynes writing about Gibbs, like a strong contrast between the physical nature and the anthropomorphic nature of entropy was well understood by Gibbs before in 1875. So, yes. Now, I think, or we think, Katie and I think, like that this is too quick. In fact, we can keep a means-relative approach to thermodynamics, but without making the jump to saying that heat, work, and entropy are anthropocentric, or in any relevant sense depend on our ability to distinguish, on our knowledge of the system. Now this is now in the next part I will talk about this, how we can keep this means-relative approach, but without going into, or basically I will talk about how having a means-relative approach to thermodynamics does not commit us to having an anthropocentric approach to thermodynamics. And to do that, it's worthwhile to define a bit clearer what is actually meant by means-relative approach. So we say that laws of thermodynamics restrict the set of processes a system can undergo. And this is like the way I introduced the first and the second and the third law. Sorry, the third law I didn't talk about. The first and the second law earlier. This is how I presented them as well. And by a process, we mean a process that is specified by an operation O that you can perform on the system, and a set of thermodynamic state variables with which characterizes the thermodynamic system. We also have the thermodynamic state space, the equilibrium state space, which is the equilibrium state space, which means that in some way we do need external intervention to the thermodynamic system. We need to push the thermodynamic system out of equilibrium if we want to make sense of thermodynamics itself. So this means that we do have an agent implicit, but like an agent doesn't need to be any human. It has nothing to do with knowledge. It is just an external system that performs operations on the thermodynamic system, and potentially measurements, but like measurements is like an entirely different thing. So now then, the means-relative approach to thermodynamics is about which processes a system can or cannot undergo. Given a set of operations O, an agent can perform on a thermodynamic system, specified by a set of variables x1 to xn. So why is this not anthropocentric? The first is that we have defined entropy relative to something, that is true, but we don't need to define it relative to the mind that perceives it. In fact, it is, when we look closer at what's being said here, it's just that we're defining it relative to a set of macro variables, x1 to xn. But having a quantity that is defined relative to another, to a certain set of variables, or relative to other quantities, does not commit us to that quantity in some way being less objective, or that quantity in some way being subjective. One example from there are many examples. One example is from thermodynamics itself. Like equilibrium, for example, is only defined relative to a set of variables that are non-changing in time. It doesn't mean that equilibrium is subjective. And then kinetic energy as well is only defined with respect to a given reference frame. So here we have something that again is defined as a relative quantity, but that is not subjective. Nobody would say kinetic energy is anything subjective or has anything to do with the mind that perceives it. So relativity itself is not sufficient for anthropocentrism. So now you might say, like, well, okay, but like, what about the choice of variables? Surely, surely the choice of variables is determined by the knowledge we have of the system. You know, Alice is assigning a different set of variables to the thermodynamic system than I am. So doesn't that make it, in some sense, dependent on our knowledge of the system? But again, like, this does not, like, this is a step you may take, but you need not, like, you don't need to take it. So the choice of, like, instead of understanding the choice of variables is determined by the means, which are in turn determined by the knowledge of the system, you might as well understand the choice of variables as a choice of description of the system. So you're deciding to describe the system in certain terms as opposed to other terms. And there's nothing subjective about preferring one choice of variables over another. So even though in some cases then there might be something arbitrary involved, like it's not subjective in the sense that it's anthropocentric. An example is, imagine you're trying to describe the movement of an ant, and then you're not going to describe the movement of an ant by describing all the molecules and how the molecules are relating. You're making a choice about what variables you're looking at when you're describing the ant. In particular, you're making a choice about this splitting up the joint system of ant and environment into a system of ant and environment. And we're making this all the time. And in particular in quantum mechanics, we need to make this. In order to speak about the system, we need to make a split between the system and the environment. And usually when the system is entangled, this will involve some kind of coarse graining, as is involved in thermodynamics. And whether this coarse grained description is happening out of free choice or out of necessity. So the necessity being we just don't know anything else about or we don't know anything else about the system, or free choice being we just want to describe the system in this way because it seems the most useful way. That doesn't really affect whether or not we think thermodynamics is anthropocentric. Okay, I'm talking too fast, I'm out of breath. So the choice of variables, description by coarse-grained set of variables x1 to xn is it's understood. Thanks, Roman. It's understood as quantifying a lack of knowledge, and this is exactly what we deny. It's like just because you're choosing a certain set of variables over another doesn't mean that this has anything to do with knowledge itself. Okay, so let me have a preliminary. I don't know how long am I supposed to talk?
50. About 3, say.
Okay, good. So I just give a very preliminary summary here, which means that to just summarize what I've talked about so far. One of them is that the means relative approach developed as a response, was developed as a response to the violations of the second law that we saw in the kinetic theory example. Thank you.
Sorry.
Perfect. No, thank you. No problem. I also could have just spoken slower, so okay, no problem. If we understand means as being determined by an agent's state of knowledge, then we do slip into the anthropocentric view of thermodynamics. And of course, in the case of Jaynes, for example, this very much plays into his game because once we start talking about the Gibbsian statistical mechanical entropy and talk about probabilities in classical mechanics, it's very convenient to have this idea that probabilities are understood in abstract terms. So, so if we understand the means as being determined by states of knowledge, then we are slipping into anthropocentric waters, but we don't need to. And if we understand the means as being determined by the levels of description we choose to describe the system and the set of operations we have in order to we can perform in the system, then we don't have anything worrying the anthropocentric here. We still have something a bit arbitrary about it potentially for the coarse graining, but this is not something that is absent in other parts of physics or in other physical theories. Okay, there are some limitations to this, and one of them is the approach to equilibrium, the minus first law that I was talking about earlier. For this, this is kind of working in the background of thermodynamics, so it's the minus first law and the second law are very much about the systems themselves. They're not, it's like hard to describe them as what an agent can and cannot do on the system, which is the description we chose for the first and the second law, and then you can also use it for the third law. But in order to understand the minus first law, the approach to equilibrium, we really need statistical mechanics. And in the following, I will try to go a bit into quantum thermodynamics. I have some extra slides if people are interested in it afterwards, but I will just limit myself to the approach to equilibrium in quantum thermodynamics to see how the same idea about coarse graining and the set of operations we choose leads to the thermodynamic spirit in quantum mechanics. Okay, so for the quantum mechanical approach to thermodynamics, for quantum statistical mechanics to work, we have two basic requirements. The first one is that it is in fact meaningful that we identify thermodynamic entities with expectation values. Now, this introduces probabilities, which is very much contested and which people don't like, especially in the classical case. In the quantum case, it's, well, I guess it would say either less or more problematic, depending on what your take on quantum mechanics is, but at least probabilities are already inherent in the quantum mechanical formalism itself. So we do have, so it's not as problematic, we're not imposing them on the theory itself. The identifying thermodynamic entities with expectation values is also not very useful for making predictions about individual outcomes of experiments, or even possible outcomes. And a good way to think about this is like if you have a fair die and you throw it many times, the expectation value is like 3.5. Like 3.5 is not even a possible outcome for the fair call. So expectation values tell us something about the system, but like they're silent about other things, namely about what an individual outcome of an experiment is. The second requirement is, so we're going to need heat reservoirs. So Fermi wrote the definition of a heat reservoir as like a body which is at the temperature T throughout and is conditioned in such a way that it can exchange heat but no work with its surrounding. It's called a heat reservoir of temperature T. Now, the characteristics are the heat reservoir can exchange heat with its environment but not work. And it's characterized uniquely by its temperature. And the temperature changes in the heat reservoir are negligible. I don't think this is very problematic. We use this in thermodynamics all the time. In fact, there was even by Clausius and Carnot and Kelvin, heat reservoirs were like a substantial part of deriving the second law in the first place. But it's useful to keep this definition in mind for where it's going to come now. Okay, so let's discuss the approach to equilibrium minus first law. So in quantum thermodynamics, the equilibrium state, sorry, I should have written state and not distribution, is the canonical state, which is given by rho beta. You know, the question is like, the question that comes up also in classical statistical mechanics is like, how do we justify? How do we justify that this in fact is the thermal state? And the way I'm going to do it here is by following Moroni's approach in his great paper, The Physical Basis of the Gibbs-Neumann Entropy, which I can recommend to anyone interested in quantum statistical mechanics, is by looking at the phenomenological thermodynamics. So looking at what we were what ingredients we have left over from phenomenological thermodynamics. And one of them is that we know that bodies. The second law was derived by considering bodies that undergo cyclic processes. We know that we were talking about heat and work in terms of, or this work in terms of a weight that can be lowered and raised. And we also we know that we have available heat reservoirs at different temperatures. So this is all from this phenomenological thermodynamics, from what we saw in the first 5 minutes of this talk. So a heat bath then, as was just explained, is a system which can only exchange heat but not work with the environment. And it turns out that in the quantum mechanical equivalent would be a passive system, which is a system from which no work can be extracted by unitary operations or unitary transformations. And so these systems are called passive, which means that you have a system and no unitary, you can apply it, or sorry, you can't extract work from it, from the system by unitary operations. And it turns out that the canonical distribution over there is a unique, completely passive ensemble. And by completely passive, I mean that an assembly of passive systems itself is also passive. So you take the product state of many passive systems, and you still want to not be able to get any work out of it by applying unitary transformations. And for this, the canonical ensemble is the unique completely passive transformation. So now, just like what I've been doing here is, I have now restricted myself implicitly, well, now I'm making it explicit, to unitary transformation. Unitary, so just as in thermodynamics we're looking at a set of operations like, inserting partitions or squeezing, these kind of things, like now I'm just looking at the unitary transformations. So then we can model the thermalization. This is what I meant by the approach to equilibrium between two systems. Then by having our system and letting it interact with the subsystems of the heat bath we just constructed out of these different canonical ensembles. Sorry, out of this assembly of canonical states, and we do this by just like having it in contact with one subsystem and then taking it apart and like putting it into contact with another subsystem and taking it away. And at each point here, we're tracing out the environment, which means that eventually the system is going to approach the canonical state. So now let's introduce the von Neumann measure. So this seems a bit ad hoc, but it will become like a bit clearer why we're doing this in a second. Then for a fixed G rho, so the von Neumann, this is just now, I mean, the von Neumann entropy is minus trace roll-up rho, so now we're just saying, considering trace roll-up rho. But for a fixed energy, the von Neumann measure is minimized by the canonical distribution. So this means that we can construct this equality here, where beta is, well, we haven't interpreted beta yet, but it's going to be 1 over the thermodynamic temperature, and this is the Hamiltonian of the density of the state rho, and we let the system interact with the heat bath at a certain temperature. This is what we just saw where we put the system in touch with the heat bath several times. And then we will see that the system state approaches rho beta, so it approaches the thermal state. And now just taking the equation before and now understanding G, or rewriting G in terms of the von Neumann entropy, minus trace rho log rho. And I think given that I'm running out of time, I will maybe make this a bit brief and not go too much into the details. We can see, so just maybe look at the final thing, we can see that we have a positive flux into the system if the temperature of the system is lower than the temperature of the environment, of the heat bath. So we have now shown in a way that there's that energy is flowing from a hotter system to a colder system. And from this we can derive the Clausius inequality, and we can derive an entropy increase. But I just forget about these details. I mean, the reason I was bringing this up is also what we usually see in quantum thermodynamics, like the proof of the second law is really in de facto exploiting the fact that the phenomenon entropy is subadditive, which means that the phenomenon entropy of a joint system, that's the system rho 1, 2, which consists of like two subsystems, rho 1, rho 2, is always less or equal than the sum of the entropies of the individual systems. And this is because there's some kind of coarse graining involved when we're doing this. So imagine we have two systems that are in the beginning not interacting, so they can be written down as a product state, and we evolve them forward in time by unitary operation, and they get correlated or entangled, and form this new state, rho dash. Then we can see that due to subadditivity, we would see that the entropy of the sum of the entropies of the subsystems will have increased after they have correlated. After they have been allowed to interact with each other before. So this is what is often called the second law in quantum statistical mechanics. But in fact, like what's happening here is that we're just tracing out degrees of freedom. So it's just a kind of coarse graining, and it's just a kind of coarse graining that we saw earlier as well. Okay, let me just briefly summarize the talk. So the main conclusions are the jump from a means relative approach or an anthropocentric approach to thermodynamics. The jump from a means relative approach to an anthropocentric approach of thermodynamics is, as we see it in the literature by Maxwell, Gibbs, and Jaynes, is just too quick. Thermodynamics itself does not need to be understood in anthropocentric terms. Instead, we may consider thermodynamic entities as relative to a set of thermodynamic parameters and operations, which means we can leave out the humans, and we don't need to consider it to be anthropocentric. And then finally, quantum statistical mechanics may be understood similarly as referring to a level of description which is given by the coarse graining that's constantly happening in quantum mechanics when we have systems entangled and we want to describe the subsystems. We need to perform some kind of coarse graining, and a choice of operations. Namely, in this case, we were only looking at unitary operations. Okay, thank you very much for your attention.